Okay, that's the title right here. Linear approximations and differentials. Linear approximations and differentials. We may be able to finish today, we may not. Okay. Let's go back to a graph that we've seen before many times at the beginning of the class. And this is a function f of x. And of course, this is what? Of course, it's p, yes, of course. And of course, this is x, and this is, of course, thank you very much. And of course, there is a point very, very, very close to it. And you will say, it doesn't look like it. I agree, because I need to explain what I'm doing. Yes, it must be q. And this, the x-coordinate of q, it will not be x plus h. It will be x plus a little bit of x, which is that particular h, but now we change the notation. So this is dx or delta x. I'll explain what this means in a second. Okay, can anyone tell us what is this? F of x plus dx, or f of x plus delta x. It doesn't matter, it's the same thing. So the right here, it's f of x plus dx or f of x plus delta x. So dx, delta x. You can say, you're changing notation again. You had this delta in the epsilon delta, true, but this is the lowercase delta. This is the uppercase delta. They are both delta, but this is lowercase delta. So we use delta in the epsilon delta definition, but this is something else. This is an uppercase delta. Okay? Same letter, actually. Good. So every time, if you remember, we had that, I'm going back to that problem with the cost. We want to find the cost of producing the 101st item, right? So this is like dx or delta x. So dx or delta x is the change in x. I no longer want to produce 100 units. I don't want to produce 100 units, but I want to produce 101. So there is a tiny change from x, not from 100 to 3,000. I can do that. What I'm trying to explain is it requires a delta x or dx tiny. So if I have just a difference of 1, it's okay. I'll explain what we're doing in a minute. So delta x is tiny. Okay? So if I want to change x, even by 1 unit, that will make a change in the y values. Right? So if I have x, I get f of x. But if I have x plus a little bit, even if it's a little bit, it will trigger a change in y. Right? Even if this point is extremely close, this change will trigger this change in y. So what would be the exact change in y for a delta or dx change in x? Exact change in y or function. So the exact change in y or in the function for a delta x or dx change in what? In delta x dx will be a change in an x. No. So this is the cost function, and this will be the change in cost. So I want to determine the change in the cost function created by a tiny change in exactly. Tiny change in x. Can anyone give us the exact change in x. How will I find it? That is called delta y. That is the exact change in y for a change in x, minor change in x. Can anyone tell us what it is? So let's go back to the graph. And can anyone say it's this? And give me a formula to write. So this change in x triggers this change in y.
Delta y.
Yes. Yes.
X plus d of x minus f of x.
Excellent. That's what it is. So it's f of x plus dx minus f of x. This is the exact change from the cost function, if you remember. This was c of 101 minus c over 100. Is the exact change in the cost for that extra unit that we want to manufacture. You agree so far? You do or you don't? Yes? This is what we did in the previous sections. Good. Now let's come back to our figure one more time. Okay, so I would like to draw a tangent here. And please tell me if I can determine the slope of this tangent. Slope equals what? Excellent, thank you very much. Of course, the slope of this tangent at P must be f prime of x, whatever that x is. If it's 100, then I'll plug in 100. If it's 105, it's 105. F prime of 105. Excellent. I'm going to extend the tangent. I'm going to extend the vertical line through Q. And I am going to form a right triangle. Right here through P, a horizontal through P, and a vertical through Q. And this is a right triangle. Also, on our drawing, I would like you to tell me one more time, what is this distance and how do we call it? Thank you very much. Perfect. Now stay with me. I'm going to take this triangle out and I'll come back because I want to talk about it. So we have this triangle now. This is point P. This is point Q. This is a right triangle, of course. You already told me that the slope of this line is f prime of x. We already know that this piece is dx. And my question to you would be in a second, what is this? What does that equal to? Don't answer just yet, because I have one more question. Forget about the fact that the slope of this line is f prime of x. I'm covering it. So from here, could you please tell me how do I determine the slope of this line? The slope of the tangent at P. That's why I took that triangle out of the picture. The slope of this line must be rise over run, correct? So it's rise, which I'm trying to identify, over dx. But I also know that this equals with what Braden said a minute ago. He said f prime of x, correct? So we knew that the slope of this line is f prime of x, but also we were able to determine the slope of the same line from the right triangle as rise over run. Agreed? Yes, please, Chris?
It might be a little semantic, but should this slope be like f prime of p?
Say it again.
Shouldn't the slope be like f prime of p?
No, P is the name. P is
Right,
the
but
name
it's-
of the point. So it's P prime of x. It's P prime of
Okay,
x.
that makes sense, yeah.
Right, I cannot plug a point in a function, right? I can plug in its x. But you're right. Yes, at P, correct. I plug in x in f prime to determine the slope of this line. Better? Perfect. Always stop me if you have something, always. Okay, so now, looking at this, forget about this, forget about the graph, forget about everything. Look at these two and say, I know the rise cannot be anything on the planet, but, and I'll put it in.
Yeah.
Exactly. 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 It cannot be anything else. Now you can say you tricked us a long time ago. And I'll say, yes, I did. Sort of. I didn't. I didn't tell you that dy has a certain meaning and dx has a different meaning. I just said you can use this notation or that notation. But now I'm showing you what they really mean. But I didn't do it before because we didn't come up with that. We didn't have this topic yet. So yes, dy has a specific meaning. dx has a specific meaning. Put together is the derivative. But they also have special meanings. What is that? It's still the change in y or a change in x, but it's not the exact one. It's the one that I determine using the derivative. It's not the exact. It's not that. So now let's go back to the graph. And I'm going to write down all these in a moment. So what is this piece then? What is this? Between the horizontal through P and where the vertical through Q and the tangent at P meet. What is this? Exactly. And now you can say, wait a minute. This one is so much bigger than that one. No, it's not. How come? Well, Q is here. It's not. It's here. So therefore, delta y and dy are extremely close to each other. Because this point is here, not here. I have to zoom in to explain what I'm doing. But P and Q are extremely close. So then, delta y approximately the same with dy. So let's write in words what dy represents, because we did not write it yet. dy is the approximation, I should say, of the exact difference in the y or the function created by a change in x. Is the approximation of the exact difference. It's not the exact difference created by the x, comma, using f prime of x. Can anyone give us from here? Can anyone solve this equation for dy? So then dy equals, I want to solve, say it again. Yes, it's just that we write, it's okay, it's perfect, but we write f prime of x dx. F prime of x dx. And this is called the differential of y. So dy is the differential of y. Why is it called differential? It's a difference using a derivative. Differential. It's a differential of y. So coming back, delta y approximately dy. Can anyone refresh our memory what I should write on the left-hand side of this relationship? What is this equal to? Yes, the exact change, but what is it in mathematical terms? F of dx minus f of x, and the right-hand side, f prime of x dx. Now, this is extremely important. And one more step, I'm going to move f of x to the other side of the squiggling symbol. F of x plus dx is approximately f of x plus f prime of x dx. And now you can say, this is so beautiful, but where is it applied? So here it is. Let's suppose I'm looking on page 255. Page 255. Well, let me choose. Let me let you choose. We want to start with a simple example on where this is applied. So use a linear approximation or differentials. We are going to use differentials to estimate the given number. What would you like to estimate? 1.999 to the fourth power, e to negative 0.015, the cube root of 1001, 1 over 4.002, sorry, tangent of 44 degrees, the square root of 99.8. Please choose any. Which one? Which one? E. Okay, very good. And that is problem 24 on page 255. So this is e to negative 0.015. No, we're not asked to put this in the graphing calculator. We will at the very end to see how close we are. No, we're not asked to do that. We're asked to use differentials, this formula that we developed ourselves, to estimate this. So the left-hand side is this. I have to identify the function. I have to identify what x is, and I have to identify dx. And then the rest will follow. So looking at comparing these two, what will you say the function is? Is it tangent? Is it sine? Is it a cubic? Is it a log? It's an exponential. Very good. So the function is definitely e to the x. Very good. Then, remember x is a number, a solid number, an integer, and dx is a tiny change from that. Like, for example, 100, and this is 1. 0, and this is 0.2. 5, and this is negative 0.3. So now, looking at this, I have to identify x and the minor change from x. And x has to be an integer or a natural number. So look at x plus dx. Look at this. X is 0 indeed, and dx must be negative 0.015. The left-hand side is done. We discovered everything. The function that we are using to estimate, in this particular example, must be e to the x. X must be 0. The minor change from 0 is this tiny number, negative 0.015. The left-hand side is done. Now I have to discover the right-hand side. So what will this be?
0.
It will be f of 0, right? This will be f of 0 plus this will be f prime of 0 times dx, which is negative 0.015. So this is this piece, and this is this piece. Almost there. I need to find f prime of x, which luckily is e to the x. And I have to find f prime of 0, which is one, and I also have to find f of 0 from here. F of 0 is how much? 1. Very good. Now let's put all pieces together. You didn't know you could find e to a number without a calculator. You had no idea. Now you can because of calculus. So then what will you tell me to write? I'm not saying that this will be an exact, this will be the exact number. It will not. But it will be such a good approximation, and you will be very proud of yourselves. So what do I write? I have to write 1. Yes. I have to write f of 0, which is 1. Excellent. And then I have to write, since I'm multiplying by a negative number here, I'm going to write negative 0.015 times f prime of 0, which is 1. You had no idea that you were able to subtract 0.015 from 1 and get e to this number, did you? So this is 8590. Do you trust this? You should, but let's not for a moment, and let's take a look. E2, let me clear all this. E2, parentheses, you know me already, negative 0.015, and enter. Are you happy with the answer? Very happy, right? Very happy. Could you have done this by hand? Absolutely not. No one can do e to negative 0.015 by hand. But now we can because of calculus. So this is one illustration of this special relationship. It's all coming from delta y, approximately dy, only if there is a tiny change in x. For something big, we can't. So if the difference is between 100 and 1,000, this method doesn't work. It requires dx to be tiny. And then the left-hand side will be very close to the right-hand side. Okay, so let's look at another example. Now, things get more complicated, of course, when we talk about word problems. So let's take a look. The radius is, for example, 34. The radius of a circular disk is given as 24. So we have a disk, it's a circle, and we have the radius that is 24. We're going to write this down, all the information like we always do. So it's given as 24 centimeters with a maximum error in measurement of 0.2. I need you to tell me what is 24. I need you to tell me what is 0.2. X, and 0.2 is dx or delta x. Same thing. Very good. Let's read on. Use differentials to estimate the maximum error in the calculated area of the disk. So before we read part B, let's take notes. So this is problem 34 on 255. And this is a true real-life application. The radius of a circular disk is given, so 24 centimeters, okay, with a maximum error in measurement. So if you want, we can write x equals 24 because we got used to x and dx, or we can write r. And dr, you already told me, is 2 centimeters, 0.2, I'm sorry, 0.2. Or you can write dx equals 0.2. One or the other, it's up to you, it doesn't matter. Yes? Did I do something? I always do something. Okay. Use differentials to estimate the maximum error in the calculated area. They are not asking us to find the exact area. Not delta A. This is the exact. They're not asking us to do that. How will I find the exact? The exact will be the area of x plus dx minus the area of x, where x is 24 and dx is 0.2. This is not what they are asking us to do. They say use differentials to estimate the error in the area. In other words, they want us to find this. Okay, one more time. Use differentials to estimate the maximum error. in the calculated area of the disk. Where do we start? We're talking about this, sir. Exactly. Pi r squared. Now we have to make a decision. Do we use x or do we use r? X, very good. So then we have a equals pi x squared. Perfect. I need to find dA. Do not confuse this with related rates. So this is a function. It's a function of x. And we want to find a prime. A prime of x is, I meant I didn't mean that. I meant dA equals just a prime of x times dx. I don't need that. I don't need to write the a prime again. So let's differentiate. We want to determine dA. Can anyone tell us what to write on the right-hand side for dA? dA equals, we differentiate a prime. We want to differentiate pi x squared. 2 pi x times, that's it. This will be the estimate of the maximum error in the measurement of the area. All I have to do now is plug in the numbers. 2 times pi times x, which is 24, times dx, which is 0.2. One more time, use differentials to estimate the maximum error in the calculated area of the disk. So what do I get? So 2 times 24 is 48, multiplied by pi, and multiplied by 0.2. Measurement unit, please. 30.16. Say it again. Indeed, is the error in the measurement of the area. Perfect. Okay, part B and part C. What is the relative error? So one more time, this is the estimate, the approximation of this, of the exact. If you want to determine the exact, you will calculate this, and subtract them. And you should be very, very close to this. But we were only asked to find the estimate. Next question is asking us to find the relative error. The relative error is the error divided by the area. Relative, so it's the error relative to the original. The error relative to what? To the original, divided by the original. So we have several ways here. This is the one I like. I write that dA is this formula, 2 pi x dx. And I write that A, of course, is this formula, which is pi x squared. And I simplify first before I plug in the numbers. Although you can determine the area with 24 and then plug it in here, it's more work, I think. We simplify pi and pi. We simplify x and x. And here's what we get. Twice dx over x. Remember, x is the radius. So the relative error in the area is twice, what is this? If dA over A is the relative error in the area, what would be dx over x? The relative error in the radius, or x. So this is the relative error in radius. Relative error in the radius.
Is the 2 not included?
Say it again.
Is the 2 not included in that?
Oh, it's 2 times. I separated so you can see that the relative error in the area is twice the relative. Yes, this piece does not go into the relative error. The relative error is only dr over r. So this is twice as much. And now we can calculate it. dx is 0.2, x is 24. The relative error does not have measurement unit. How come? Here's why. This is measured in centimeters squared. This is measured in centimeters squared. And we simplify centimeters squared. No measurement unit. So what do we get? So 0.4, I'm sorry, divided by 24. What is that? 0.016. 0.01667. No measurement unit. Final question. What is the percentage error? I just have to change this into a percent. Percentage error. Of course, in the area. It's 1.667%. And that's it. So these are applications of the fact that we can, with calculus, we can estimate an exact difference. If x has a minor error, we can estimate the exact difference using differentials. We don't have to determine the exact difference if we're happy with a minor error. If it's a life and death situation, medication or other things, maybe you will not be happy with any error. It makes sense. But if you're happy with minor error, then this will always be easier than this. If you want to determine the change in the y value or the function, this will be your best bet for a small dx than this. So I know I only have 2 minutes left. I just want to find a couple of problems for you to work on from 3.9 for Thursday. Okay, on page 248. On page 248, 17. Um, 9 also, 9 and 17. And on page 255, let's say problem 25 and 27 on 255.